talk today about artificial intelligence tools and other automated systems for camera trap image management. Thanks to the organizers of CIBIB, the conference, for inviting me to talk today. If you want to read more about the Road Ecology Center, you can do so at roadecology.ucdavis.edu. So the premise of my talk today is that there are many organizations throughout the world, including my own, that are employing camera traps to monitor wildlife presence and movement. And we're collecting millions of images while we're doing this every week or month. And image processing can be one of the most labor-intensive steps in that use of camera traps, followed by collecting SD cards from the cameras and all the way through to creating knowledge from the images. So automating steps in that workflow could really help us reduce cost, labor, effort, and so forth in the whole monitoring using camera traps. In the talk today, I'd like to acknowledge several people, Christian John and David Wachin at the Road Ecology Center, and Jeff Gagnon and Haley Nelson at the Arizona Department of Game and Fish for supporting this work over the last 5 years and being a great partner in doing this work. So camera traps, we use them a lot of different things. Relevant to what I'm going to talk about today, we look at occupancy and monitoring occupancy of wildlife and modeling their occupancy, evidence of their presence. We also use camera traps quite often to monitor movement of wildlife through structures, either structures that were built for the wildlife, especially, or structures that were built for some other reason, like moving water or a road. And the wildlife are just opportunistically using that structure to get from one side of a roadway to another. There are a lot of limitations to camera traps, or several limitations to camera traps. The first is sensitivity. They have a range of sensitivities, but if you have a very small animal, then it's really constrained by, your use of camera traps is constrained by the size of the animal. There's a limited cone or zone of detection, the area that can be detected by the camera, whether it's from the sensor or the size of the image and what's in the field of view for the camera. There's often limitations of range, or there's always limitations of range. So for example, with the sensor for wildlife movement, could have a 20 or 30 meter range where it can be triggered. Then resolution, like with any camera, there's going to be limitations on the resolution, and meaning how fine-grained of a picture you can get, which then interacts with how much you can say about an animal that is present in the image. The devices aren't terribly expensive, but they're still $100 or $200 each for the ones that we use. And that does limit the size of the array or the number of cameras you can put out into the field. But that's also constrained by the cost of data management and the complexity of data management. So the more cameras you have, the more would be spent on managing the data flow through staff time, for example. So what I'm going to talk today about is how we can reduce those costs by automating different steps in the overall workflow. The system, the umbrella system that I'll be talking about is what we call CAM1, CAM for camera, and then WON, WON, Wildlife Observer Network. And the URL, the website address, is on the screen. It's a system open for anybody to use. There are 57 projects that have collected data on 140 species, used by 87 different organizations across those projects. And it can be used by volunteers or agencies, academics, anybody, for managing wildlife camera images. And at the core of this system is a database where the image collected by the camera trap is the record. It's the center of the database. And what this means is that instead of having the image sort of ancillary off to the side, maybe it's referenced as being available or there's a link to it, it's really the center of the record. And treating the image as the center of the record, as the foundation of the database, brings with it a lot of requirements. So there's a lot of benefits of doing that, but there's also a lot of requirements. This requires a lot of database organization, fairly massive storage requirements. So for example, if you had a series of images and for each image you had a row in all of your data is in an Excel file, maybe you'd have 100 megabyte, 200 megabyte Excel file, which would be a pretty big file, and equivalent to 100,000 or 200,000 images. And that amount of storage requirement for just the Excel file would be about 0.1% of the storage requirement for storing all the images. We store all the images, so the storage requirements are very high. And you should know that if you're ever going to use a system like this. So the idea of the images record is that the image plays a role in the database, and the data model for the system is shown on the right-hand side. And what we mean by a data model is the architecture of the architecture of the database. And so the boxes here describe different aspects of the database. For example, the animal image identification, what's the animal event, what is it doing, the location of the camera, and so forth. So these can all be part of the database, the data model. And associated with that would be something like this map view down here at the bottom, showing the position of the cameras, the geolocation, which has a corresponding box in the data model. The EXIF data associated with an image shown here, which is the metadata which all camera traps or smartphones collect about any image, the date, time. If you have location on, you would have the coordinates for the location that the image was taken, and this EXIF data database. And then finally, the image. The image provides a lot of different attributes that can be collected. The primary one being what is the identification of the animal, but it could also be how many animals are there, what is the animal doing, and so forth. You can think about the database as sort of the endpoint of collecting the data. And so that's shown on the far right of this diagram. The beginning of the whole process is obviously the camera. The camera is triggered and it collects an image for an animal, hopefully. Sometimes it's just blowing grass. And one thing that we can automate is how the camera collects the images and sends them to the database. And so this diagram shows one pathway that we've used that's a possible pathway where a camera is either a cell communicating camera or a Wi-Fi communicating camera that sends the image with the EXIF data, and the EXIF data and the image are used to create a record in the database. So shown here on the x-axis are the different aspects of that. There's a field component, the camera's in the field collecting images. Communication, the camera's sending, in this case, the data by cell network or Wi-Fi. The server, which is the home server at UC Davis, where the data are collected and processed, and then the database, where the database records would reside. So in this case, the camera takes the picture, sends it through cell network, let's say. The EXIF data is read and record is created. And the only thing that's really left is to identify the species or the number of animals and so forth to create a final record in the database. So really the steps between in this pathway. The more traditional pathway is that you have a camera takes a picture, it ends up on an SD card, and someone has to go into the field to the camera and collect the SD card to collect the images. Typically, what someone might do then is to open the SD card on a computer, maybe copy the images off, go through every image to see what animal is present, record those images as records in a database, like an Excel file or a relational database, to create that database record. We've automated some of those steps. So this is a manual step, collecting the SD card. There's then a second manual step we have, which is to zip the contents of the SD card into a zip file, a compressed file. And then we have a special tool, which I'll be talking about in a moment, called Image ID, where the zip file is uploaded to this web tool. And this web tool, Image ID, determines which images contain animals. Very important step. You only want the ones that contain animals. It gives you back another zip file, which you can then upload into the CAM1 system and automatically create a database record. And then that leaves the remaining step of identifying the species. So this process is somewhat similar to the very manual process most people undergo, but there's a lot of automated steps in terms of creating the record or finding the images that contain the animals in them in order to reduce the total amount of time it takes to process the images. The endpoint is always a final record in the database that has the species ID and is based around the image. One of the most important and difficult steps process is to find the false positives. And those are the images where you have moving vegetation or car positive, where there's no animal present in the picture. Sorting through all of those and finding out which ones are the false positives and which one just contain the animals obviously can take a lot of time depending on what's in the field of view. It's very manually intensive effort, so therefore it's costly to hire people to do this. Computationally, it's also fairly difficult to have machines or computers set up to find those images, but it's possible. And so if you have a setting like this one where moving vegetation could trigger the camera and there's sets of pictures with or without animals, positive images and the true positive, the ones containing the animals. So the way that we do this is using a machine learning solution. Machine learning is often used interchangeably with artificial intelligence. Basically, it's a way for, in this case, computer vision applications to look at patterns and determine or learn from a series of patterns what is in the image so that you can correctly predict. So it's very helpful in image classification for detecting objects in the view, for classifying those objects in the view. And therefore is very useful for images which have patterns in them. The two primary steps in this process, the first is to train a model. So you would build a candidate model, say, okay, I think this model could be effective. And then you would train it with a series of images. So over here on the right, you have what we call tagged images, meaning that we know what's in them. And so you might have a stack of images, and this could be 10, 20, 30,000 images of the same type of animal. And then you might also have a stack of empty images, and it's useful to have empty images from the same cameras so that you can do kind of a reciprocal training of the model, showing when it's an animal present and when an animal is absent. You go through these iterative cycles of training and testing models until you've found a good model, the one that seems to work with the training and testing data. And then you can use this model and challenge it with novel images, meaning new images that you've collected to predict the type of animal or type of event in the picture. And so the output of this process is a classification of an animal in an image, would be a classic result of this process. So there's a lot of different tools out there that are currently available. I'll talk about three that we tested, two that we tested that other people developed, and one that we developed ourselves. And the first one here on the left is a mega detector developed by Microsoft. And this is based on what's called FastRCNN. FastRCNN is convolutional neural network device or tool built in R. And there's different fast variants. There's a faster and a fast, but basically they're set up to use what are called convolutional layers which take a series of images and develop what's called proposals for what's in the image, which can then give you a classification of what's in the image. So it's a very stepwise process. Another tool that we tried out is called MLWIC. This is the reference for that tool, and any references listed here that people want, just email me and I'll send them to you. I'll try to find them and send them to you. It's based on ResNet 18 architecture, which is also a convolutional neural network approach. And so you can see these are the layers in the convolutional neural network. And basically you have a similar kind of training and classification process with this tool. This runs in R and was published 2 years ago and has been tried out by several people yet, but not extensively. And then finally, there's a tool over here on the right, a custom detector for mule deer, 6-layer convolutional neural network built in what's called TensorFlow in the Keras library. And this is a Google system that is free to use, free to download and install. It probably costs to train somebody to use it. And it uses input images and convolutional layers to train the model, test the model, and then develop an output. So these are some of the results from testing these tools. And we used 2 main types of tests. One was speed and the other was accuracy. And this is showing speed. And the result of the speed test is using 8 sets of 100 images, so 800 images from cameras near a highway project. We looked at the impact of pixel count, which is basically the size of the picture, and substrate complexity, meaning how complex is the background, how many different objects are a very simple background or very complex background. And what we and our mule deer classification tool were very fast, on the order of milliseconds, less than a second for each image, compared to megadetector, was relatively slow. And for megadetector, the more pixels there were, or the more complex the background, the slower the tool ran. So you might think, well, that means maybe megadetector is not that great. Well, megadetector actually turned out to be really good when it came to accuracy. And so this shows 2 different measures of accuracy, precision and recall. And the number 1 on the y-axis would be right here, and here, and here, is perfect. So that's what you're really looking for. 1 means highly accurate. In general, there weren't very many significant effects of the image size, pixel count, or the complexity, substrate complexity on accuracy. And our mule deer tool worked pretty well. But MLWIC with complex images able to identify animals very well, and with large pixel counts was also not able to identify animals very well. The most reliable in terms of accuracy was the MLWIC, sorry, the megadetector, the Microsoft megadetector shown here with this red line. So it's relatively slow, but it's very accurate. For the mule deer tool, this is the one that's built in the Keras library, convolutional neural network. The graph here on the right shows training the tool. We used 25 epochs or cycles to train the tool, and 25,000 images containing mule deer from 12 camera positions. And what you're looking for in this case is that the more you train the tool, so the more epochs, the higher the accuracy should be. So this is exactly what happened. The training data set is shown with the blue line, and generally you'd expect that your training data set is accurately classified. The test data set are images that were not used in the training. And what we found is that we got up to about 93 or 94% accuracy with this tool. And after about 10 epochs, more cycles didn't make it more accurate, which suggests we should possibly rebuild the tool. And then we found this other way of doing things where we constrained the training and testing system with this tool, and with more training, with the same amount of training, the same number of epochs, we actually got a tool that was close to 98, 99% accurate. So then we were much more excited about that. And remember, this is a very fast tool that takes less than a second for each image. So we eventually developed a very accurate and fast tool for identifying mule deer. Another important series of steps to automate, if you think about where camera traps are used to monitor wildlife movement through a crossing structure, the most important measure of success of a crossing structure is that an animal goes from one side to the other. So in this diagram, I've got 3 types of events that you might measure if you're using camera traps near a crossing structure. The first over here to the left, we'll call event type 1. And this is showing multiple images of the same animal from one camera. And so you don't want to count those multiple times and then you think, oh, well, I had three deer, not just one deer. So it's important to be able to turn these into just one event rather than have them be 3 events. A second type of event, you might have multiple cameras on one side of a structure and they all collect images of the same animal. And in that case, you also don't want to have multiple counts of the same animal in your database. And so being able to recognize these as the same animal in multiple pictures from multiple cameras is also important. And that's mostly crossing, going from one side of the structure to the other. You want to know that an animal you observed on this side of the structure over here is the same animal you found. All of these tasks are done manually. And those of you who have done this know that it can take quite a long time to determine if an animal crossed from one side of the structure to the other. What we've done is automate the process of comparing images. So rather than manually comparing and saying, is the deer here on January 5th at 6 p.m. the same deer as this one that was on January 5th at 6:01 p.m. in a different camera. And so we use the time, date, and location stamps to determine if an animal is the same animal on one side of the structure to avoid data duplication, and did the animal cross and was detected from one side of the structure to the other. So we can think about how we could integrate all of these systems together. And this shows some of the process for doing that. Integrated systems, this is borrowing from earlier diagrams and adding in some new parts. So you can imagine that you have a camera that collects images in the field. It automatically sends those through a cell or Wi-Fi network, which creates a record in the database. You might have a species identification tool over here, where you take those images and process them to identify the species, and then send that back to the database. Now you know what species that are contained in the images. You could then compare images on different sides of a structure around the same time to say, is it the same crossing event or is it a crossing event? Did we find the same species going from one side of the structure to the other? And then finally create a record where you've basically had an automated series of steps all the way from the camera to the final record in the database without requiring any human or manual interaction. So this is somewhat ideal. We have all of the parts. We haven't actually put them all together into one integrated system, but we have all the parts to create this integrated system. And it could save, obviously, a lot of time, many thousands of hours of analytical time just in our organization, let alone among all of the different organizations. One of the important things I kind of glossed over is the only animal we're able to identify confidently right now are deer. There are other tools that are promising for different species. And I think that if you put those together, you might be able to create something that identified maybe the top 5 or 10 common species with a high degree of confidence. So where are we going from here? One of the most important and difficult questions is which AI or artificial intelligence tool is best? There's, any paper you read will say ours is great. In my presentation, I said ours is great. So, but that doesn't mean they're great for every goal. So it really depends on the goal for your system. If you want very, very accurate classifications and you don't care if it takes a while to get there, then you might want something like Microsoft's Mega Detector or a similar very robust but slow tool, which might be enough. We found that we use Mega Detector, and we have it running full time on 2 devices, 2 servers, and we're able to support 4 to 6 analysts using about 100 cameras total. So really, the speed of the system does matter if you're trying to process a lot of data. If you're using it on a vehicle, then obviously you want a very fast tool, but you also want it to be accurate, and that's one of the difficult things for the vehicle side animal identification. So where do we want to go from here? I've talked mostly about our system, wildlifeobserver.net, where we can integrate these automated tools together, but really you could build this platform in many places and use similar kinds of processes. It's not, it's no longer a complete new invention every time. There are a lot of the tools we need out there. We definitely need more data and training and testing of these tools. I also would caution very strongly not to assume that a published tool is going to be effective for your needs, and you really need to test them extensively before using them. If you want to use our systems, just email me or my colleague David Waitin, and we can set you up. If you want to learn more about CAM1, here's the URL for CAM1 again. And if you want to learn more about the Road Ecology Center, then go to roadecology.ucdavis.edu. And again, I want to thank the organizers of CIBIV, and I'm happy to take any questions or feedback or input, et cetera, that you might have.